Build Science 101 is sponsored by Anderson Windows and Doors, Builder's First Source, Huber Engineered Woods, Polyguard, Sashco, and Durail.
All right, my friends, Building Science 101. Next up, airtightness, air control. You know, we talked earlier in the series, if you've been watching the previous episodes, about the control layers in the building. We're going to control water, air, vapor, and thermal. So this is number 2 on those control layers and is in the importance scale just right behind water management. Steve, where do we kick off on this airtightness?
You know, like we talked about in water management, I broke this one down into 3 very simple concepts, right? There's the concept of continuity. Write that up here. And basically, the concept of continuity is, and this is the key to airtightness management. Now, pay attention that we didn't call it air barrier, which a lot of people like to think about that, because the air barrier, it's far more complex in a wider spectrum than just an air barrier. It's a whole management system when it comes to air tightness.
You know, if I could make a quick point on that too, as we think about water management, water's honestly a little easier for us to think about. It's a little more visible, a little more tangible, right? Water falls from the sky, it rises from the ground.
I can put it in my hand.
I can touch it and feel it. Air's a little harder. I mean, we're swimming in a fishbowl of air right now. And if you think about this studio that we're in, or the room that you're watching this, there's so many places for air to move in and out of that room, besides just your vent on the ceiling, or maybe a window that's not closed in the back wall.
Yeah, it's a little bit more mysterious adversary than water.
That's a great way to say it, a mysterious adversary. I like that.
So continuity is the first concept. The next one would be separation. And then lastly is a word, and I used escalation.
Continuity, separation, and escalation. Should we start at continuity?
Yes, we're going to talk about continuity. Continuity is the key, right? It is the number 1 concept of airtightness. The way I was taught of airtightness is think of airtightness as a leak in a boat.
Okay.
You don't want it.
Yeah.
You don't want 1,000 little ones.
Yeah.
You don't want 100 medium-sized ones, and you sure as hell don't want one big one.
That's for sure.
Right? You don't want any leaks.
Your bilge pump's not going to keep up with a real big one, is it?
Exactly. So when we turn to continuity, and again, we're going to fall back on Joe. And, you know, for those of you that aren't familiar, Joe owns Building Science Corporation and building scientists that came down from Canada. But when you look at the family tree of building science in North America, in the United States, there's one person that sits at the top of the tree.
Joe Stieberg.
Joe Stieberg. All roads lead to Joe.
Yep.
And his comments, our learnings, our understandings, they're just different versions of something Joe said.
Something we've learned from Joe. That's for sure.
So Joe had the red line test, right? And the red line test is very simple. He said you should put your pen down anywhere on a building section, and you should be able to trace around the building. And the most important thing is that red line test should close.
It should be continuous, right?
It should be continuous.
The same word as continuity, continuous.
Exactly.
You never pulled your pen up from the plans as you were drawing.
Yeah. It should be as airtight. Now, this is a funny one because I get into a lot of verbal aggressive discussions.
It's a good way to say it. I like that.
You know, because here it comes. Some people think buildings need to breathe.
And we talked about it a little bit in our earlier series, but let's spend a minute here in case someone's watching this module first for whatever reason.
So my combative response is very simple, right? If you live in a very hot climate or a very cold climate, do you ever consider leaving your windows open an inch? All of them, right? If you live in Minneapolis and it's February, do you go around and open every window a half inch? Hell no. You close those puppies up, and on the bad windows, they're sealing plastic around the inside, right?
I grew up in a house with that.
Yeah.
My dad would go to Kmart and get the shrink wrap film for our leaky windows on my 1950s house, and we'd wrap the inside, and then he'd take a hairdryer out and shrink wrap it. And that was an extra way to keep the wind from blowing through our single pane wood windows.
So in one aspect, we go through that kind of effort. But in the same conversation, people are saying, well, buildings need to breathe. No, they don't.
No.
You just said you wanted to seal it all up. Why is sealing it up okay somewhere and sometimes, but not all the time?
That's right.
So I'm calling your bluff. I'm saying if I could build every house as a hot air balloon, I would.
That's right.
Zero air leakage.
That's right. We want it really tight. You've used this analogy before. If I don't mind, if you don't mind me stealing it from you, you think about your car, right? If you're driving down the highway in your nice car, if you had a window that wouldn't close all the way, you would immediately take that car back to the dealer and say, hey, this doesn't work. So we want our cars to seal up really tightly. On the other hand, we also, and we're going to talk about this later, we want to bring fresh air in for the occupants of the houses. This will be in a later module, so we're not going to get into fresh air right this minute. But if we can't seal up the house, we can't take control, we can't really give a good environment for that house. So this air continuity is incredibly important.
It's incredible. And, you know, we can now test for it, right? There's this thing called the blower door test where we put a shroud on one of our open doors. We seal up, we seal up everything. We put a fan in there. And then we measure the amount of air that we're running out of the house or pushing into the house. We can do a positive or a negative test, and we'll get into why we would want to do that. But we're measuring that flow across there at a certain pressure. For a blower door residential, we're typically at 50 pascals. So I've always, Joe taught me, you know, a pascal is the amount of pressure that dropping a piece of paper exerts on a surface.
Pretty low.
So it's pretty low.
Yeah.
Right? So even 50 pascals isn't a whole lot of pressure.
Not a lot of pressure.
Right? But it's what we use as the standard for our test. But basically what you're looking for when you do the blower door test is a number that symbolizes basically the amount of air leakage over the total surface area of the building. Now, when I talk about total surface area of the building, understand that is ceiling or roof. It is all of our walls, including the foundation wall, and it's the bottom. So it is all 6 sides of the box.
Yeah, and if I could extrapolate on that, we often refer to that as the conditioned space of the house. That's the envelope for the house. And that's the envelope that you're going to live in.
And we're going to get into that when we talk about separation.
Yeah.
So, but the red line test is basically, that is our management system to battle the blower door.
Yeah,
right?
and actually, I'm sorry, I forgot to, let me interrupt you for one quick second. The blower door test is not just a measure of how well we did in the house, but also in most places where you're watching this, it's now part of the building codes. And so depending on when you're watching this and where you live, there's going to be a score on that blower door test that you need to actually make. And this is coming to pretty much everywhere in North America, at least. If it's not already a requirement by code, it is where Steve builds and where I build. It may not be in a few places, but it's coming very, very soon. So this blower door, this isn't just theory. This is practice, and this is you being able to get a certificate of occupancy from your jurisdiction where you build as well.
Yeah. Now, 2 things about the blower door test. One, that you mentioned, it's becoming more prevalent and becoming requirements in certain locations. But I like to take it one step further, because when we build a house, we don't just build a slab, a foundation wall, a exterior wall, and then put a roof on it.
That's
we
right.
put windows in, we put doors in, we run electric wires through the wall, we run plumbing wires through the wall, we run HVAC lines through the wall.
Yep.
And it seems like we have more and more penetrations through our air barrier system than we have ever before.
That's right.
We have tons of stuff going through there.
For sure.
So when I do a blower door on some, and it's selective because it can get not only costly, but we don't need to do it on everyone. I do multiple blower door tests
Mhm.
because I like to see what components of the building are contributing to my air tightness,
That's right.
right? So we did a house years ago. Zip was one of the first products. It was the first time it was on the market. And so we built the box. I used it as my primary air barrier. We didn't get the windows delivered. They were delayed. So I coaxed the builder into, let's just build a big green box. And we put the drywall in on the second floor lid after we put the roof on, and it was a slab on grade house.
Okay.
So it was basically just a green box.
Okay.
And then we tested it.
So concrete slab on grade, kind of like my tabletop, walls.
Yep.
And then the framed roof had the air barrier at the top with drywall.
Yep.
Okay.
So we had our continuous air barrier, no punctures, no penetrations, no windows or doors,
Got it.
just the one door opening where we had the blower door test. And it performed amazingly well.
Super tight.
Super tight. And I used to tease the gentleman at that company because it's like, I've already done a full scale model test of your product that you guys haven't. Right. But understanding, how things work as an architect, I found it very important to me. People say, well, I build a really tight house. Well, how do you know?
Yeah.
Right. And I could sit there and say, well, I build a really tight house, but how do I know what's contributing to the air leakage I am getting? Where do I need to target my efforts as an architect and have my builder target his efforts as a builder to really get as tight as we possibly can?
Yeah, that's for sure.
Right. So, and the thing about air tightness that some people don't realize, and it's not necessarily a myth buster, but let's just say it's a knowledge evolution. Years ago, when we talked about energy efficiency, we talked about, it's real easy. If somebody says I build a really good house, I'm like, how do you know? Well, we build R38 walls, right? We do an R60 ceiling. We use R5 windows. We do R10 under the slab. So they'll rattle off all the thermal properties of the building.
And that's a good building.
And that's a good building. But we've been tuned to, because a good performing building has good thermal insulation.
That's right. Yeah.
But the reality is, when we get the blower door, and it's a game changer in the sense that now we can measure air leakage.
Yeah.
So, hey, Mr. Builder, Mrs. Builder, Mr. Architect, you guys are now getting tested.
Yeah.
Right? Your details are getting tested. Your execution is now getting tested.
That's right.
And the thing that we've learned is that while our value is important, I'm not trying to discount insulation, but energy efficiency is directly tied to how tight our house is.
And the analogy I used in a previous episode was the Yeti cooler, right? The Yeti cooler is a really well insulated cooler. And you and Jake cut one open one time to show the cross section of a Yeti cooler, really thick insulation and this really thick plastic on the inside and the outside that holds it in place. But if the lid is open on your Yeti cooler, it's going to perform no better than the $5 cooler from Walmart. The key to Yeti coolers is closing the lid, and they've got these latches that really push it down against the gasket. And if you look at the top lid on a Yeti cooler, there's this big gasket that runs continuous all the way around the lid, so that when the lid is closed and you push those two rubber levers down on that Yeti cooler, it seals it really, really tight. So the key to that high performance cooler is good insulation and good air tightness. And as Steve mentioned, that insulation doesn't do anything if the lid is open.
Yeah. I mean, and understand that air tightness is directly tied to that energy.
Yeah, that's right.
And if you don't think you're leaving your windows open, or if you don't want to leave your windows open, then you need to consider air tightness, right? And so when Passive House came to America, the movement is probably somewhere around 13, 14 years ago where it came here. And if you watch some of the earlier versions, I'm not a big fan of labels. But what I am the biggest fan of is discussion.
Mm-hmm.
And when Passive House came to the U.S., there's this set of metrics, building metrics. One of their metrics was air tightness, and it's 0.60 at 50 pascals of ACH, air changes per hour. And so That 0.6 now is a line in the sand for passive house. And I'm not here to talk about you should do passive house, you shouldn't do. My point is that for the first time in building history, someone drew a line in the sand in terms of airtight.
And so this is the goal for this particular standard, which Steve and I have seen really take off in the country. Let me also say that building codes have also drawn a line in the sand and a much looser standard, where I am currently, as we're filming this, we need to make a 5 ACH 50.
Yep.
Let me just break it down real quick.
We're at 3.
And 3. So 5 air changes per hour, ACH, at 50 pascals of pressure differential between the inside and the outside. If you could go back to that blower door example, that blower door, I like to liken to an example of a balloon. It's pressurizing that balloon, and the blower door is calibrated, the blower fan on there, so that if we know the pressure difference between inside and out, we're able to figure out how many pinholes, pin pricks, or big holes we have in this building envelope. The more the pin pricks, the more the holes, the higher the blower door score. That's where that 5 ACH 50 comes from. I've been in some older houses, some 70s houses, that almost couldn't get a blower door score because they were so leaky. They were above 10, they were above 15 ACH 50.
When we test, like, say 1950s homes or earlier in New England, yeah, we're at like 30, 40 ACH 50.
Yeah, I
like,
mean,
the fan can't even
leaky.
get a setting, right? Because you're already beyond it.
Yeah,
So,
super leaky. So this 5 ACH 50 or 3 ACH 50, which is maybe currently code, those codes are changing and they're getting tighter and tighter. I wouldn't be surprised if you're watching this a couple 5 years from when we first filmed this, that national code goes down to 2 or maybe even 1 someday. And I know the step codes in Canada are stepping that down so that those codes are going to go even lower.
yeah. And you know, the thing about airtightness is probably the first 30 or 40% of airtightness management is low-hanging fruit, right? It's just a very slight conscious effort to that building assembly.
Yeah.
And you know, hey, seal this joint. Hey, run a bead of sealant along here, or run some tape across this joint in our project there. And that number goes crazy good.
Yeah, that's right. It gets better.
And in terms of like that number, you know, if you're a builder and you don't believe in this, right, understand that 5 years ago, nobody cared about the blower door number.
Yeah.
Now we're at 3.0 and it's moving in a different direction. It's going to become harder and harder. You don't want to be the builder that has to figure it out when the requirement's 1.0.
Yeah, that's right. And honestly, it's death by 1,000 cuts in this. As you mentioned, air is really hard to understand as a concept. And so this air tightness is something that we need to focus on. And I'll be honest, I've been thinking about it for 15 or maybe even 20 years in my building career. And I've been able to get lower and lower scores, but it takes time. It's something that as a concept you need to be thinking about. And in the 201, and maybe even though we'll publish a 301 series, we'll get into very specific methods and products and examples. But here we want to talk about that concept. With that being said, let's run into concept number 2.
Yeah.
As we're talking about concepts.
As a side note, I think it's Belgium has already adopted passive house as their building code.
Is that right?
Yeah, there is a country in Europe that uses
We might have to do a
passive
401
as
series
yeah.
someday.
So we're moving in that direction whether you like it or not. But,
That's right.
All right, concept number 2. Separation. You're going to love this one. This is so fundamentally simple, but for some reason, it's one of the hardest concepts for the building industry to understand, right? If this is my red line, I am either outside or I'm inside.
This is Building Science 101.
Right? It's not rocket science, it's building science. I'm either inside or I'm outside.
You're on one side of the line or the other.
There's no gray area. There's no maybe so in airtightness. There's no kinda. There's no, yeah, we thought that's kind of like a transition zone for our airtightness. No. You are either out or you are in.
I love it.
There is nothing else to understand about air tightness management in terms of separation than that simple concept.
That's really, really good.
It is that simple. I can't tell you how many times I walk around houses and insulation goes up like 5 feet in a garage wall, and there's mechanical equipment here. And then there's like exterior garage attic that I can see into. And I asked the builder, I said, is your mechanical inside? Oh yeah, it's inside. We got insulation right there. Okay, well, the insulation stops at about 5 feet. And the drywall and stuff, it's kind of like, this is outside there, my friend. Like, you might think it's inside of that wall, but we're not talking about inside the wall. We're talking about inside the red line, right? So when I draw that red line all around the building, there's a demising point there. And it is that red line. And I'm either in it or I'm outside of it. Now, one of the other interesting parts of this to me that I get questioned on quite often is, Steve, what's the best air barrier? Right? What's the best component that I should use in my buildings? And in words that Peter Yost loves to use as a building scientist, he says, well, it depends. Why does it depend? Well, just look at this simple drawing, and this isn't even a complex one. We have concrete slab, concrete wall, we have band joist, we have above grade wall, and we have a ceiling assembly. Right there, we have 1, 2, 3, 4, 5 different components that make up our air barrier system or our air management system, right? Now, if I take that and I add a window, or I add a door, right? Or I add penetrations.
Hose bibs or
Hose bibs,
HVAC
wires, exterior outlets, right? All of those things have different systems that then get incorporated that bridge from our common what I call my primary air barrier system to those secondary components like a window.
Yep.
Put the window in a rough opening. Well, there's something across that rough opening that has to maintain, you guessed it, continuity.
Continuity. That's right.
Right? Because continuity is the key. And, so there is no, just use this or just use that, because the field of those components is not nearly as important as when two components come together and that you have to bridge that air barrier from this material to that material.
Yeah.
Right? That becomes the huge challenge in air tightness.
And on your drawing set right there, where the top of the second floor or first floor ceiling is the continuity of the air barrier, that means that that attic space above that is outside.
Yes.
Right?
Yes. Even though you see it as, hey, Steve, isn't the attic the attic inside? Well, it's under the roof. No, it's not. It is outside of my red line, unless I choose to incorporate components of the roof as part of my red line test. Then I could make a conditioned attic.
Yeah.
Now, these are the decisions that we make along the design process, right? So just like we asked when we were talking about water management and you're the client, you should be asking your builder and your architect, what is their air tightness strategy, right? Is my attic a conditioned attic or an unconditioned attic? Is it outside or inside? And they better have an answer, right? Because if you go back to the first one and my favorite word, this is the whole reason we're building. Control. How do I know, or how can I possibly gain control if I don't know what I'm trying to control?
That's right.
Right? If I can't define whether my attic is outside or inside, then don't even come to me thinking about control.
That's right.
Because you don't even know what the hell you want to control.
That's right.
So,
and as a further note on that, if your attic is outside, meaning the ceiling is your air barrier, and that attic's outside, where I am in Texas, we see a lot of mechanical equipment up in attics, which are outside, meaning it's a vented attic. You see these air vents. It's a pretty hot space. There's insulation on the floor of the attic, and the drywall is the air barrier. Well, now to Steve's point, that red line's not continuous anymore because now all of a sudden I've got HVAC equipment, I've got ducts, I've got all these different penetrations in that air barrier. And so if you watch a lot of my videos, I talk a lot about conditioned attic spaces in my houses because I don't have basements in Texas. We have a lot of rock. We have a lot of other reasons not to need it, like no frost line here. But in the north where we build, we often have, like this picture shows, a basement where you see mechanical systems. You see water heaters, you see the furnaces, the air conditioning systems, ductwork down there. That tends to be in attics in Texas. And that really goes against this concept of separating the inside from the outside and maintaining that continuity. In a quick for example, if that HVAC equipment was in that attic space, which was outside, and that were to leak some air out of the ductwork, and all ductwork is somewhat leaky, now I've depressurized my house. And we know that nature doesn't like a vacuum. So any air that's leaking out of that ductwork is leaking out of the house. The inside space means that air is going to have to come back and make up from somewhere else. And where does it make up? It makes up through all those little cuts and holes in our envelope. Sometimes that's around exterior outlets. Sometimes that's under the bottom plate of the house. But if that house is in a state of vacuum, of negative pressure because air is leaking out of that ductwork, it puts our house into a bad situation. So that continuity is really a big deal. And that's why I talk a lot about bringing our HVAC equipment into the inside space of the house.
Yeah. So, you made me think. I'm about to tell you a story where I might have pushed the conversation a little too far.
A little 201.
A little, well, not 201, but a little too insulting.
Oh, okay.
But hey,
let's do it.
I think they deserved it. Pull up a chair because you're going to love this one. All right. I stopped by Builder's building his own dream house.
Mm-hmm.
This is the house they're going to carry me out of this house, Steve. Okay. I go in the house, and just as you say, there is ductwork, there is equipment up there, all that stuff. It's in Texas. We had just left another house, a building science friend of mine. We were doing some work in the attic. That day, we measured 163 degrees in the attic.
Dang, that's
Okay?
hot.
Outside, it was probably somewhere around 100. All right, so there was a huge delta. That attic was an oven. But my point is, you're building your dream house here, my friend. Okay. You're going to buy energy. Remember when we talked about energy efficiency? We're going to buy that purchased energy. I'm going to run it through an air handler, and I'm going to chill it. I'm going to cool the air in there, and I'm going to cool that air down to, if I'm trying to deliver it to a room, I'm probably trying to deliver it, let's say 70 degrees, 68 degrees, something in there. I'm sending it down the line, let's just say at 60 degrees. I'm going to use real simple numbers. All right, 60 degrees, and I'm going to run it down the line, and I'm expecting my house to perform well. Okay? I told you to sit down. Think of the math here. That air is going down a duct at 60 degrees. It's 163 degrees in that attic.
It's not just outside, it's actually worse than outside.
Worse than outside. So this is the part where I pushed the conversation. I looked at the builder and I said, not only is putting your ductwork in the attic in Texas just a dumb idea, you should have ran the ductwork on the outside of your roof. It would have been more energy efficient.
That's true.
By 60 degrees.
Yeah.
I would have knocked the delta down to 40 degrees from 100 degrees.
Yeah.
Right? It's what baffles me about building science. And it's really the whole reason that Matt and I are doing this is when you step outside of building and you look in and just give a quick analysis of what we're doing.
Yeah. If
you
we just
realize how some ideas are just really dumb ideas.
Yeah, I mean, this is just basic high school physics, right? Moisture moves from more to less, heat moves from more to less. And should we put our ductwork into the hottest space in the house when we're trying to cool our house? It just doesn't make sense.
Yeah. All right. Last note on separation, and you touched upon it. You touched upon there's pressures that are happening at the top plate and there's pressures that are happening down here that are different than pressures that are happening in the middle of the wall. Down here, typically, because heat and air, the air is rising there due to the temperature there. It's always hotter up here than it is on a floor in any house. So what that does is it basically creates a negative pressure. The house is sucking on the lower transition points.
Is that considered the stack effect?
Yes, the stack effect is this piece here. But that air at the top is trying to go out because that ceiling area is being pressurized due to the stack effect. So if you were to graph that, it looks like this. And actually, I'll switch colors here. It looks like this. So this is air trying to get out. This is air trying to get in. So what's interesting is in the middle field of the wall, there's not a whole lot happening in terms of air tightness,
Pressure.
and air leakage due to pressure, right? So somewhere in there is what we would call the neutral pressure plane. And the neutral pressure plane is where that negative pressure and that positive pressure equalize, right? Or are neutral. They cancel each other out.
Yep.
So what does that mean if I'm a builder or if I'm an architect? Well, while these details are important here, the ones that are more important are these and those.
That's a very great point.
Because that's where that challenge, that Mother Nature's challenge, is happening.
They're going to experience the most escalation, right? Which is your concept 3 of the airtightness.
Yes, that brings us right into escalation. So these details are escalating more than that detail. But the basic premise of escalation is the minute I introduce an airstream to a building, well, things can jump on that airstream. And this is why air tightness and water management are linked as control layers, right? Joe had that really cool image that I know you've seen. It's a piece of drywall, right? And he has a 1-inch square hole in it. And it's something like, diffusion, moisture migrating through a material. It might be 1 cup of water. You cut a hole 1-inch square, and it's an order of magnitude. You get 100 cups of water that can move through that 1-inch square.
Because of the air.
It gets on the air train, right? So that moisture jumps on the air train. Now, if I'm in Minnesota, somewhere out here, let me switch colors here. Somewhere out here, I might find a cold surface. What happens with nice, warm, moist air hitting a cold surface? Changes the water. And guess what? Our air tightness neglect has now become a water management problem.
All right, the backside of that sheathing.
The backside of the sheathing is raining.
Yeah, it might be cold in Minnesota because it's 10 degrees outside, and inside the house is warmer and moister because we've got people breathing, we're cooking, we're showering. And so that 1-inch hole in the drywall, as that air moves through that 1-inch hole, now all of a sudden we can have moisture problems inside the wall.
And I've illustrated it here as a very simple example, but I'll give you another one. I investigated a building. This is a house that was in excess of $20 million to build. Okay. The house has about 5-foot overhangs and it has these nice swooping roofs. And what's happening is on the face of the fascia, they were getting all kinds of staining there. And they were these brown, ugly, like zebra tiger stripes on all of the fascia. And you sit there and you go, okay, what's happening? Well, at first glance, you might think, okay, well, it's got to be water bringing it, but it's not a water management problem. It's an air tightness problem. Because in that 4-foot overhang, you can imagine, a person can crawl through here, right? It's a pretty big opening. But when we look at the materials, there was a slate roof. The slate roof was over paper, over plywood, and you had the exterior wall here. So the exterior wall is leaking air. That leaky, moist air getting into this cavity. Guess how nice and warm the backside of that plywood is in the winter in New England?
Cold.
It's cold. So that water's condensing. But it's not only condensing, it's condensing on the backside of the plywood.
Mm-hmm.
Well, what does that mean? Well, plywood is wood. Wood has wood sugars. Those wood sugars mix with that water to make a real, I'll be nice, crappy brown look.
Kind of like a tea almost.
Like a brown tea. And guess what? Because it's sloping, that water runs right down here. It finds cracks. It comes out here and it drips off of the fascia.
Mm.
But when it does it, it leaves that residue on that fascia board and it creates those tiger stripes.
Yeah.
And this isn't a problem with the fact that they use slate. This is a whole series of little things that air leakage through here had the ability to escalate due to all these other parts of that assembly.
So good, Steve. There really is no gray area, is there?
There is no gray area. Remember, I'm going to show you again because I can't tell you how many times I go out to the building and I can ask a builder. And if you're a homeowner, walk around your building. If you question it, if you cannot answer as a homeowner when you're standing somewhere in your house, am I inside or outside? Call your architect, call your builder, set up a meeting and say, hey, I'm standing here. Would you both say I'm inside the building or outside the building? Because I'm either inside or I'm outside. There's no gray area.
Yeah, that's right.
It is that simple. Remember, it's not rocket science, it's buildings.
I'm going to make one last point, even though I know we should be finished. But in his example here with that attic, that means that attic needs vented. If that was a front porch, if that was a soffit area that was beyond the air barrier, we'd also want to vent those spaces. Because if we did have any moisture buildup, we'd want that moisture to dry out. And this is a building code issue, and this isn't really a building code series, but any space that's outside needs to be vented. This episode of Build Science 101 brought to you by our friends at Polyguard. Now, this may be a name that you don't know because in the past, I've made a lot of videos. In fact, they're one of our very first sponsors. You've heard me talk about Polywall, and you've seen me make a lot of videos about Alumaflash and Blue Barrier. Polyguard is the parent company, and they've done a bit of a rebrand. They've sunsetted that Poly wall name as a brand family, and some of the individual product names are changing as well. Same products, same great company. They've been around for 70 years, and they make some really bomber products. Steve, have you used any of the Polyguard products before?
You know, I was just recently introduced to them, Build Show Build Boston. Our whole foundation system is coated with the Polyguard products. And the thing that I like about it the most is it's a systems approach to waterproofing, right? They could have very easily just made the waterproofing and said, hey, here's a great waterproofing, have at it. But they provided a dimple mat. Yep. And it's not a dimple mat. They provided two different dimple mats because they understand that the water accumulation at the bottom might be greater than the water accumulation at the top. That's right. So they have a totally different mat. Yeah. They have their Blue Barrier product for that cold joint between the wall and the footing. So it's really great when there's companies out there that understand that there's a differentiation in risk, right, between the wall and that cold joint, and that they develop products accordingly, create the system that as an architect and a builder, we can put faith in. And, you know, a basement is not something you want to dig up a year later to try and find a leak. So you have to put a system in there that we trust and we believe in, and one that's going to work. And they have their barrier system, but that dimple mat offers that water management on the outside of it, so it doesn't even really get challenged.
Yeah, and this really ties in perfectly, Steve, with our Build Science 101 series. Steve and I have been talking about how water is the #1 enemy, the #1 killer of buildings, whether that's groundwater, rainwater, water that splashes back against your house because you didn't put gutters on, whatever. So when we talk about these products that Polyguard make, these are really bomber products that are going to protect your house for the lifetime. Quick story with these guys. About a dozen years ago, when I kind of stopped using house wrap, I realized I needed to up my game. I ran across this product called Alumaflash, now UV240. Peel and stick, aluminum facer. I recognized that another really good builder in town was using it. Here we are more than a decade later. Every well-built custom home in my town is wrapped with this silver facing, which is the Polyguard product. The builders that are doing the really good products here in the South recognize this is the absolute best, most bomber way to build her house. So that being said, big thanks to Polyguard for sponsoring today's video. All kinds of products that we didn't even get to mention. Go check out more at polyguard.com. Steve,
I'm gonna let you close it out, but you just talked about vented roofs. So guess what we're talking about next?
how about that?
Vapor management.
Vapor management. This is a really big one. There's a lot of mistakes and there's a lot of problems in old buildings with lack of vapor management or lack of thought.
You want to talk about mystery.
It's for sure.
Vapor is the biggest mystery.
That's true.
Building.
Vapor is a really mysterious one. So next episode, vapor control. With that being said, we'll see you next time on The Build Show.